So what we're comparing here is weight with the cube of the height. So our comparison is directly between weight and h cubed, height cubed. The little squiggly symbol, the tilde, is a traditional symbol used in variation problems. It just means it's by comparison. But we can turn this into an equation, but to do so I need one more letter. And now I can't say that weight is the same as height cubed. You know, that wouldn't make any sense. But I can say that W is equal to K times h cubed. So letter K is called the constant of variation. It's also called the constant of proportionality, but I think I'll stick with constant of variation since this section is called variation. And it's a number which shows up in all these problems that has to be calculated. And what it represents, it's sort of a link to the specific problem you have. You know, this problem works for this species of tree. But if you had a different type of tree, would weigh differently, for example, then K would have to be different. If you applied it to anything else that grows or can be of different size, you know, weight is always varies according to the cube of the height in anything that grows. And so the K would have to be calculated differently for each specific problem. So now we're going to be able to figure out K from this information. A 5-foot tree weighs 20 pounds. And so that tells us that the height is 5 feet when h is 5 feet when the weight is 20 pounds. All right. Now I didn't write the units in here. I'm making an exception to my normal policy of writing units on everything. The one nice thing about these variation problems, you don't have to worry about computing with the units, provided that you're consistent on both sides. You know, for example, if you changed if one side was in feet and you changed the other one to inches, then you'd have to worry about units. But as long as you keep the same units within each measurement category, then we're okay. We don't have to worry about it. I do want you to write units in your answers, though. That's important. But literally, height is 5 feet when weight is 20 pounds. Now, if you were in engineering or something and studying these problems, you probably would write in those units because the K becomes interesting to engineers and their problems. And why is that? You know, because engineers, they design things. And, for example, how strong a certain object is they're designing may depend on the materials they're using. And so they can look up these K values in their books and gives them values for various kinds of materials. And so anyway, that becomes important to a scientist and engineer, perhaps, the units of K. But in here, I think we're okay just working it like this. All right, so a 5-foot tree weighs 20 pounds. So I'm going to plug these numbers into here. And let's see, 20 goes for W. K is 5 cubed. And so let's solve for K. Now, I would solve by dividing both sides by 5 cubed. So K is, and by the way, this cancels, so K would be 20 over 5 to the third power. I've seen a lot of people screw up this step. You know, solving these little tiny equations. You know, people get in a hurry and they think they know how to solve equations well, and then they totally botch it. So, you know, don't underestimate these little tiny equations. Be careful of what you're doing. I've seen, for example, people would do this. They would say, transfer this 5 cubed over here, so K would be 20 times 5 cubed. No, to solve, you got to divide by 5 cubed. All right, now, what are we going to do with that? We can simplify that fraction. and which is fine. I tend to leave them multiplied out a lot of the time, but here this simplifies nicely because you know, 5 cubed is 125, and I can reduce this fraction to let's see, be 4/25. So k is 4/25 reduced. Incidentally, k works great as a decimal here because 4/25 is what is that, 0.16, I believe. It's an exact decimal, and but I would discourage that much of the time unless you're willing to write a lot of decimals, because we'll see problems where if you may have a k may be like a very, very small decimal number, and if you cut it off too soon, if you round it off too short, then you're going to create big errors. And I think it's, you know, when the fractions are easy, just write the fraction and we'll deal with the decimals later when you're punching on calculators. Alright, so I tend to work these with the fractions. Sometimes I don't even multiply all this out, and you'll see why later as I work some of these problems, why that would be okay. Alright, so let's see. We use the second sentence, which I think of as a calibration for this equation we're building, because we are building an equation that fits this problem, and we have to calibrate the constant variation with this second sentence here. 5-foot tree weighs 20 pounds. And now that we figure out what k is for this problem, we can plug it in, and w equals to 4/25 times h cubed. So this right here is not, we're not done with the problem, but this is called the equation of variation. And so you might think of it as a formula that we derived for this problem, this equation of variation. And what's nice is that we can reuse it over and over. We can recycle it and plug in different size trees if we wanted to. In this example, you know, if we want to know what a 20-foot tree or a 37-foot tree would weigh, we could estimate it with this equation of variation. It would work out quite nice. All right, now we're only going to apply it once because the third sentence just asks us to apply this equation of variation. So what would a 10-foot tall tree weigh? All right, so now this, when you translate that, that means, this last sentence means find W when, let me fix that. Find W when h equals to 10 feet. All right, well, I can just plug 10 feet into h. So W is 4/25 times 10 to the third power. And let's see, that would be, this is 1,000, so I have 4,000 over 25, and that divides off nicely to 160. So, as predicted earlier, it was supposed to be 160 pounds because twice as tall, twice as wide, twice as deep is 8 times the volume. 8 times 20 is 160. So that sort of confirmed that that conclusion earlier. Finally, I want you to write the answer in English. And so a 10-foot tall tree would weigh 160 pounds. All right, now to be specific, you know, this is really an estimate because, you know, even if it's the same species of tree, suppose it's a spruce, for example, or an oak, one that's twice as tall is going to be shaped a little bit differently. It's going to have different kinds of branches and so many leaves. But this is a pretty good guesstimate. I mean, it's would probably be pretty close to true, provided those trees looked about the same, with the exception of their size. So anyway, there's sort of an introduction to this whole language of variation. And you know, this is quite a valuable tool in the sciences. and I'll talk more about that later.